Hello, it's Eugen. As you see, I finished my converters. Some of them are fully finished, some are in process yet. And now I faced such an interesting problem as how to test them. Most of Gauss builders or simply producers of converters from, for example, automotive accumulators to grid voltage, you can find a lot of such videos and photos in the net. They simply connect incandescent lamp to the output of a converter, and if this lamp is lighting, the lighter the better. They say it's okay, the converter is functions in the right way. But we know that when our converter is intended for charging a massive capacitance, it works in non-equilibrium mode during a most of time of charging. In the beginning it is close to the short circuit at all. So if we need to test such a converter in a proper way, we should have some device which approximates our aim circuit, for example gauss-gun. So this video is dedicated to the process of testing of such a converter, how to do it in a proper way. Okay, this is the circuit which I elaborated to test my converters. It consists of 5 simple ICs. The main of them is this double operational amplifier, or it may be 2 separate amplifiers. Here I wrote down some types which can be used. Nearly every amplifier can be used here. The circuit functions as follows. When the voltage on the output capacitors of the converters under charging is low, it is fed here through this high ohm resistor and this divider, which can be trimmed with this potentiometer, and it goes to the non-inverting inputs of the amplifiers. So in the rest, the output of the amplifiers are low, and they switch this timer to the off state, so it has a low state on his output too, and it goes to this timer which bears only inverting function. It is driver inverter in this circuit, and so this output MOSFET is switched on. This MOSFET must be high voltage type. I used IRF 450, for example. And this commutates the capacitors under charging to the ground through this discharging resistor. This is big ballast resistor. I collected it with some, as far as I remember, 9 pieces of powerful resistors. I will show you in the next part of this video. And also the voltage through this divider, high level voltage, goes to the input of the converter and switches it off. Okay. When we press this button start, low level goes to the input, through triggering input of this timer, and switches it on. So the output here goes low, the MOSFET is closed, and the converter is started, and the voltage begins to rise on its output. And in this input of my circuit, and when it reaches the level which is trimmed by this potentiometer, the second operational amplifier goes high, We can see it with these diode lights, and this timer is switched off, and the output of the circuit returns to its initial state. So the switch, the power MOSFET is open, and the converter is shut down. So discharging begins through this ballast resistor. In my circuit, it is about 100 ohms, so accompanied with 3000 microfarads of the capacitors under charging, it makes about one third of second time constant. So the capacitors are fully discharged in about second or two. This switch turns the scheme into Freckle mode, as I called it. It means that this timer driver shuts down, so the switch also is shut down, and this timer begins to generate a rectangular signal with a very high duty cycle, which goes to the controlling input of the converter. So the converter begins to work with a very low duty cycle. Its power is about 2% of its nominal value. So the voltage on the capacitors begins to build up rather slowly, and it allows us comfortably trim the level of work of this amplifier, which can be controlled with this lighting diode. The last switch here, this button, discharge button, it allows us to discharge output capacitors if we need it for some reason. The threshold voltage is fed from this linear regulator. It is simply 7805, for example, and it is also used to supply this timer with 5 volts. The input voltage of the circuit, which is used to supply it, is about, it may be from 9 to 15 volts. Okay, let's look how it works in reality. Oh, one moment, I forgot to tell about this diode. It is used to bias the inputs of the operational amplifiers into their common mode range. There is such a value in datasheet, and it is useful for amplifiers which cannot work with common mode equal to ground. Nearly every type of diode is suitable here. I used 14007 with a low leakage current. Okay, so here is a finished device. You can see a ballast resistor. It consists of 9 powerful resistors of 25 watts and 100 ohms each. They are connected in 3 groups. Each group consists of 3 such resistors in parallel. So the total resistance is 100 ohm, and total power is about 250 watts, 225. Here we can see realized circuit, which I told you about in the previous part of this video. Here are 3 timers and operational amplifier. 2 buttons. This button connected to the gate of the switch. The power switch itself is under the PCB here. And this button starts the pulse mode of the circuit. Here is the switch which switches our circuit between Freckle mode and cycle mode. Okay, Let us switch our circuit on. Now we can see two lighting diodes. It is this diode indicates the supply, and this diode is connected to the gate of our switch. So now the switch is closed, it is on, and so the these output capacitors of our converters, it is my old battery, consists of 7 electrolytic capacitors for 450 volts and 470 microfarads each. So it is about 3030 microfarads in total. And now they are connected to ground through these ballast resistors. Our converter is here. It is supplied in his digital part from through this tail from our circuit, so we don't need another battery for digital supply. We need only one battery now. It is connected to the power circuit of the converter. Okay, now we should start our scheme. We switch it on power supply. You can see green lighting diode on the converter. Here it is. Okay. And okay, now we will switch our circuit into the frequency mode, and I'll show how to trim the level of voltage. Okay, you see that voltage is building up slowly. It is so slow that we can comfortably trim this potentiometer to achieve level of voltage which is desired for us. This level, as you remember, one of this operational amplifier will switch on and stops charging. Well, now it is about 200 volts. As you can see, it is very slow build up and rather comfortable for us. Well, according to my calculation, it is about 250 volts when it will start. Okay, you can see this red diode light, so let us trim it for some extent. So with this simple procedure we can set our desired voltage level in a range of about 250 volts to any level up to breakdown voltage of our switch. It is 500 volts, but we have 450 volts maximum voltage of our capacitors and about 420 volts limitation on our converter. So I am intended to test my converter at about 400 volts maximum voltage, i.e. we are going to cycle it to 400 volts with fast discharge and repeat this procedure for some times. Okay, building up is very slowly. I think that I will modify my circuit to speed it up for some value. You can see this character sounds from the transformer. It corresponds to pulses which are charging our battery. Well, we are close to our, let us, okay, it's 400. Now it's fast, it is fast discharged. Okay, so now we can test our circuit in in a mode close to its exploitation in gauss-gun. When I press this button, it will be fastly charged to 400 volts, the value which we trimmed just now, and then very fastly discharged to 0. Let us try it. Okay, that's all. We didn't see exact value on our voltmeter because it was very fast, but we know that we set 400 volts and it reached it just now. We can at once touch our switch and monitor temperature on all parts of our scheme, because it is fully discharged in about 1 second. Okay, all functions as it must. So now, for example, I am intended to build Gauss gun with, for example, 8 shells. So we will charge our capacitors, fire, then charge, fire, and so on for 8 times. Now we will see how our converter will survive this procedure. Okay, let's begin. 1, 2, 3, 4, 5, 6, 7, 8. Okay, let us touch our switch. It is hot. I think about 90 degrees Celsius, but is touchable. It's rather touchable. Transformer is warm, but not so warm. Output diode is cold, and current sensing resistor is warm. Okay, our converter survived our test, and these modes are, I think, just what they are needed here. Why? Because if it had blown up or broken, it is of course very bad. It said us that we made a big mistake, did wrong calculations. But if it had been cold, if our switch was cold, it said that we chose our components with a big excess of price, because we could take, for example, cheaper switch with more internal resistance, and for example we could take another output diode with smaller current limitation. And now, as it is warm, all components are warm, but they didn't blow up, it says us that we made the right choice and the construction is optimal. Okay, so I am intended to use this test rig for all the rest of my converters, and then I will plan to build them into some Gauss guns or rail guns, whatever I will construct in nearly future. Okay, thank you very much. Goodbye.